Imagine handing over $1 billion, like in cash,
Right.
every single month.
Just an astronomical amount of money.
It really is.
Hmm.
And you're not doing this to buy a competitor or, acquire some revolutionary new startup.
You're not even inventing a new technology with it.
No, exactly.
Yeah.
You are handing over $1 billion a month simply to rent the right to plug your computers into the wall.
Yeah, literally just for the electricity and the space.
Which is wild. But that is exactly what one of the most powerful tech giants on Earth is doing right now, today, out of sheer desperation.
It really highlights a massive shift. I mean, we've spent the last decade, maybe longer, treating software as something ethereal,
Right. We call it the cloud.
Exactly, the cloud. And it sounds so weightless and infinite and just completely invisible.
Like it just exists in the air around us.
But the reality of artificial intelligence, especially right now, is that it is heavy industry. It's concrete, it's steel, it's massive turbines spinning in rivers. And it requires a staggering, just an almost incomprehensible amount of electricity.
Which is why we are doing this deep dive today, so welcome. Today, we're looking at a fascinating stack of notes centered around a really detailed analysis from a blog post dated June 2026.
By Paramendra Kumar Bhagat, right?
Yes, exactly. The piece is titled Netizen, Himalayan Compute. And this source, it really unpacks this invisible crisis that's happening right now.
Because everyone is so focused on how fast AI is getting smarter.
Right, the algorithms, the new models.
Yeah, but almost no one is paying attention to the brutal physical limits of just keeping those machines turned on.
And our mission today is to really explore the multi-billion-dollar lengths that these hyperscalers, these massive tech companies are going to, just to find the cheapest, most abundant power in the universe.
Because the underlying premise of Bhagat's analysis here is that intelligence is no longer constrained by the software.
It's not the code anymore.
No, it's not the sophistication of the algorithms or even, honestly, the manufacturing capacity of silicon foundries.
Right.
The ultimate bottleneck of the AI era is literally the electron.
Just raw power.
Yeah. And the desperation to secure that power is completely rewriting global economics.
Which brings us back to that billion-dollar monthly bill I mentioned at the start.
Let's unpack that.
Yeah, to understand the sheer panic in the compute market right now in June 2026, the source points us to this blockbuster SEC filing from June 5th.
Which is just wild to read.
It is. So Google has entered into a cloud service agreement with SpaceX.
Right.
Google is paying SpaceX $920 million per month for access to compute capacity.
Almost $1 billion every 30 days.
Yeah. And we have to look really closely at what that $920 million actually buys them.
Because it's not what you'd think.
Right. They are renting roughly 110,000 NVIDIA GPUs.
Plus the networking and all the supporting infrastructure.
It's exactly. Housed inside SpaceX data centers. And the timeline on this, the full rate kicks in around October 2026 and runs through June 2029.
Though they do have a 90-day termination option they can trigger after December 2026.
Right, a little escape hatch. But the source also mentions Anthropic is doing something similar.
Yeah, the Colossus One deal.
Yes, reportedly paying around $1.25 billion per month for capacity, which involves even more GPUs and upwards of 300 megawatts of power.
Which is just a massive facility.
But I really want to focus on Google for a second, because this is the part that kind of breaks my brain.
Okay, lay it out.
Google practically invented modern internet infrastructure, right?
Absolutely.
They designed their own custom AI chips, the TPUs.
Yep, the tensor processing units.
Right. They operate one of the most sophisticated, globally distributed server networks ever built by humanity.
No question.
So why on earth is Google paying a rocket company a massive premium just to rent hardware?
It seems backwards.
It really does. It's like, I don't know, it's like a major airline like Delta or United suddenly buying thousands of seats on a competitor's flights at this massive markup just to put their own passengers in them.
That analogy actually captures the mechanics perfectly, though.
Really?
Yeah, because when an airline does that, like if they actually rent another airline's planes, it's because they can't get their own new planes delivered fast enough.
Oh, I see.
And they simply cannot afford to let their passengers defect to a rival airline in the meantime.
Right, you lose the customer, you might lose them forever.
Exactly. And in the compute market, this concept is called bridge capacity.
Bridge capacity.
Yeah. Google still owns their proprietary frontier models, their data, their secret algorithms.
The actual brain of the AI.
Right. But SpaceX owns the physical hardware, and this is the crucial part, they own the energized facility powering it today.
Let's break down the unit economics on this, because the math in the source reveals the true scale of the premium Google is paying for this bridge.
The math is staggering.
It really is.
Yeah.
So if you take that $920 million and divide it by the 110,000 GPUs.
That comes out to roughly $8,364 per GPU per month.
Right. And assuming a standard, 720 hours in a typical month.
That is an effective rate of about $11.62 per GPU hour.
Okay, $11.62. And the context for that number is what makes it so striking.
Oh, totally. Because if you look at the open market, major cloud providers might charge anywhere from maybe $3 to $11 for a high-end H100 equivalent GPU instance.
So 11.62 is already at the absolute top of the market.
It's beyond the top. And if you look at the specialized GPU bare metal markets, places like Vast.ai or Renpal.
The spot markets.
Exactly. You can often secure these exact same GPUs for $1.50 to $4 per hour.
Wait, really?
Yeah.
So Google is paying a 2 to 5x markup compared to the spot market.
Yeah.
So why not just do that? Why not just rent 10,000 GPUs from one vendor, 20,000 from another vendor in Europe, and just piece it all together for $3 an hour?
Because of the physics of training a frontier model.
Okay, explain that.
You simply cannot train the next generation of a massive language model on a fragmented, piecemeal network of GPUs that are just scattered across different data centers around the world.
Why not? If the math gets done, doesn't it all just sync up?
Because the computation requires constant, instantaneous communication between every single chip in the cluster.
Yeah.
This is what they call the all-reduce operation, where the model updates its weights.
Right, the learning part.
Exactly. If the chips aren't connected by ultra-high bandwidth, incredibly low latency networking fabrics like InfiniBand housed in the exact same physical facility, the entire training run just grinds to a halt.
Because it's waiting for data from the other chips.
Yes. The GPUs will literally just sit idle, drawing massive amounts of power while they wait for data to travel across the country.
Okay, so you need the whole orchestra physically in the exact same room playing at the exact same tempo.
That's a great way to put it.
You can't have half the string section playing from a studio in Ohio while the percussion is playing over a Zoom call in Texas.
Right. The latency would completely ruin the symphony.
Makes sense.
And building an orchestra pit large enough to hold 110,000 GPUs, all wired together perfectly, takes years.
Years.
Yeah. So Google is paying that 11.62 rate not for the silicon itself, really.
They're paying for the room.
They're paying for guaranteed enterprise scale capacity that is unified and available immediately.
Because time to market in this AI arms race is basically measured in months.
Exactly. Slipping a year behind a competitor could mean total obsolescence.
You're just out of the game.
Right. And SpaceX had the unified infrastructure ready to deploy right now, and they're basically charging a massive toll road fee for it.
And to Google, avoiding a build delay of even just a year is easily worth that billion-dollar monthly premium.
It's the cost of staying relevant.
But that really begs the fundamental question here.
Which is?
Why does Google have a build delay at all? I mean, they have endless capital. They're the best engineering talent in the world. If the problem was just laying concrete and buying some server racks, they could do it in their sleep.
They absolutely could. But the source argues the bottleneck has fundamentally shifted.
Okay.
We are no longer living in an era of silicon scarcity. The foundries in Taiwan are pumping out the chips.
So we have the chips.
We have the chips. We have entered an era of power poverty.
Power poverty.
The constraint isn't getting the GPUs anymore. It's getting the electricity to actually plug them into.
We really have to look at the power draw of these specific hardware architectures to understand why the grid is just buckling under this.
It's unprecedented.
Right. A high-end AI GPU, whether it's an H100 or the newer Blackwell and Rubin architectures, consumes an immense amount of energy.
Oh, yeah. A single chip, just one chip can, draw 700 watts to well over 1 kilowatt of power.
Which is crazy, just to wrap my head around that. 1 kilowatt is roughly the power it takes to run a microwave oven on high.
That is a great visual.
And we're talking about putting 8 of these chips, so 8 microwaves, running on high into a single server unit.
8 chips per server, plus all the CPUs orchestrating the workload, the high bandwidth memory, the networking switches.
All in one box.
Yeah. A single server node can easily demand 10 kilowatts.
Wow.
And then you stack those nodes into a standard rack, and suddenly a single server rack is drawing 100 to 120 kilowatts.
And just for context, what did a normal, older data center rack draw?
Traditional data centers were built to handle maybe 10 to 15 kilowatts a rack.
Oh, wow. So it's 10 times more dense.
Exactly. The density of power required per square foot has grown by an entire order of magnitude.
And drawing that much power creates a massive secondary problem, right?
The heat.
Exactly. All that electricity going into the rack has to go somewhere once the computation's actually done.
Right, because the laws of thermodynamics dictate that every watt of electrical energy consumed by a processor is ultimately converted into thermal energy.
It just becomes heat.
Pure heat. And if you do not remove that heat instantly, literally instantly, the silicon will exceed its thermal limits and physically destroy itself.
It just melts.
It melts down.
Yeah.
And the source notes that cooling accounts for 30 to 50% of a data center's total power budget.
Because traditional air cooling, like just blowing big fans over the heat sinks, that no longer works at 120 kilowatts a rack, right?
Not even close. Air simply does not have the thermal mass, the specific heat capacity, to carry away that much thermal energy quickly enough.
It's like trying to put out a campfire with an eyedropper.
Right. Which is why the industry is being forced into direct-to-chip liquid cooling.
Where they run water or coolant right over the metal.
Exactly, pumping chilled fluids directly over the processors. But chilling that liquid, running the heavy pumps, and then rejecting that heat out into the atmosphere via these massive cooling towers.
All of that requires immense auxiliary power.
Yes. You're using power just to manage the power you used.
The International Energy Agency, the IEA, actually ran the global projections on this, and the numbers are just staggering.
They really are.
In 2024, global data center electricity use was around 415 terawatt hours.
Oh, okay.
The projection for 2030, so just a few years from now, is 945 terawatt hours.
Which is hard to even visualize. But to put that into a tangible context, 945 terawatt hours is roughly equivalent to the total annual electricity consumption of Japan.
An entire G7 nation's power grid, dedicated entirely to servers.
It's wild.
Which really brings us to what the author terms the dual constraints facing the AI industry.
Right, the two walls they are hitting.
Exactly. The first wall is still hardware manufacturing, to some degree. These chips require high bandwidth memory, which involves incredibly complex packaging of stacked silicon, and that creates a production bottleneck.
True.
But the hyperscalers, Google, Microsoft, Meta, they have the capital to monopolize that supply chain.
Right, they just buy their way to the front of the line.
They secure the chip allocations. But the second wall, however, is the utility grid.
And the utility grid does not care what your market cap is.
Exactly. You can't just bribe a power line to carry more voltage.
No, physics doesn't take bribes. You can have a warehouse full of newly delivered Blackwell GPUs, but if the local utility grid is tapped out, those chips are useless.
They're just very expensive paperweights.
Basically. The interconnection queues, the wait list to get plugged into the grid in the United States and Europe are currently stretching out for 3 to 5 years.
3 to 5 years just to get permission to plug in.
Yes. And it is not just a lack of raw generation capacity at the power plants, It is a lack of transmission infrastructure.
So it's like buying a massive fleet of 100,000 exotic sports cars, parking them in a giant dirt lot.
Right.
And then finding out the nearest gas station has a 3-year wait list just to run a hose out to the property.
That is exactly what it is. And you can't just build a gas station overnight.
Right.
The source highlights the severe supply chain constraints on heavy electrical equipment.
Like what?
Specifically, high-voltage transformers.
Okay, what do those do in this context?
So these are massive industrial components required to step down power from the super high-voltage regional transmission lines, the big towers you see on the highway down, to a lower voltage that the data center can actually use safely without blowing up.
Got it. And there's a shortage of those.
A massive shortage. They have multi-year backlogs. The manufacturers simply cannot build them fast enough.
Because they take a lot of raw materials, copper, specialized labor.
Exactly. So you have tech giants with literally billions of dollars in silicon sitting idle, turning into stranded assets, simply because they cannot secure a transformer.
Which perfectly explains the SpaceX deal from the beginning.
It brings it all together.
SpaceX had the power secured and the facility completely energized.
They had the transformers.
Google paid the premium for the electricity, not the silicon.
Exactly.
But, the author doesn't frame this as a catastrophic, permanent roadblock for human progress.
No, he's actually pretty optimistic about what this forces us to do.
Right. They frame it as a demand signal, a catalyst for an energy renaissance.
Because markets respond aggressively to absolute constraints.
Right.
When the most capitalized companies in the history of the world suddenly require hundreds of terawatt hours of new continuous power, It creates an unprecedented economic incentive to just build energy infrastructure.
The money will find a way to solve the problem.
Yes. The author draws a really interesting parallel to the history of solar power, specifically referencing Wright's law.
Wright's law. That's the one that observes that unit costs fall as cumulative production increases, right?
Exactly, the learning curve. The more you build of something, the better you get at it, and the cheaper it gets to make the next one.
The source notes that in the 1970s, solar modules cost over $100 per watt.
It was a total niche technology,
Yeah.
used for satellites and calculators.
But as global manufacturing capacity scaled up, prices plummeted by roughly 20% for every doubling of cumulative volume.
And today, solar costs have dropped by more than 99%.
Wow.
It makes utility-scale solar the cheapest source of new electricity generation in many parts of the world.
So the author argues that this insatiable hunger for AI compute will act as a hyper-accelerator for clean energy broadly.
Because these tech companies are signing massive power purchase agreements, PTAs.
Right. They are essentially subsidizing the entire energy sector.
They're guaranteeing a buyer for every single megawatt a developer can bring online.
Whether that's massive new solar farms, geothermal projects out west, or even pushing the regulatory boundaries for things like small modular nuclear reactors.
Right. They are injecting pure capital directly into the base layer of human infrastructure.
Because they have to.
Because they have to. The AI boom forces innovation in grid management, in high-voltage direct current transmission, and in utility-scale battery storage.
Which is great for the world eventually.
Absolutely.
But that is the long-term, decade-out optimistic view.
Yeah, that doesn't help Google tomorrow.
Exactly. These tech companies have to train their next-generation models today. If terrestrial power grids take 5 years to upgrade, and the waitlist for transformers is longer than the actual lifespan of the chips themselves, where do you find a completely unconstrained environment?
Well, the source outlines a proposed solution that sounds, frankly, completely absurd.
It really does.
Until you look at the physics.
Right.
Orbital AI compute.
Putting the data centers in space.
Yes.
Which is just, it feels like sci-fi.
It requires a massive mental pivot, sure. But the physical environment of low Earth orbit, or LEO, technically solves the two most binding terrestrial constraints: power generation and grid interconnection.
Okay, walk me through that.
Well, if you deploy a satellite cluster in what's called a sun-synchronous orbit, for example, the solar arrays are exposed to sunlight almost continuously.
Oh, because they're up high enough to avoid the Earth's shadow mostly.
Right. You don't have to deal with the day-night cycle, weather patterns, clouds, or atmospheric attenuation that reduces solar efficiency down here on Earth.
So it is just raw, uninterrupted solar energy. And crucially, there is no utility board in space.
No zoning committee.
No neighbors complaining about the noise of the cooling fans.
Exactly. And there is no queue for a transformer. You generate the power on the satellite's solar wing and pipe it directly into the server rack 3 feet away.
But surely the environment of space introduces massive new problems.
Oh, absolutely.
Let's talk about cooling.
Right.
Because you mentioned earlier that cooling takes up to 50% of a data center's power budget on Earth.
Right.
Space is incredibly cold, right? You're absolute zero.
Yes.
So cooling should be basically free up there.
See, that is one of the most persistent misconceptions about space engineering.
Really?
Yeah. Yes, the ambient temperature of the void is incredibly low, but space is a vacuum.
Okay.
It is entirely devoid of matter. There are no particles. On Earth, we remove heat from processors using conduction and convection.
Meaning what, exactly?
Meaning we heat up water or air that is physically touching the hot thing, and then we move that heated fluid away into the atmosphere where it mixes with other air.
Right, like blowing on hot soup.
Perfect example. In a vacuum, there is no air to blow on the soup. There is no air to carry the heat away.
Oh, so if a massive cluster of GPUs is generating, 100 kilowatts of thermal energy and there's no air to absorb it, what happens?
The heat just builds up in the server chassis until it literally melts into slag.
It just cooks itself inside out.
Exactly. Unless you utilize the only method of heat transfer available in a vacuum, thermal radiation.
What do you mean?
You have to emit the heat away as infrared light. You literally glow the heat away.
Huh.
And radiative cooling is notoriously inefficient compared to convective cooling.
Like how inefficient?
Well, the efficiency of a radiator in space is governed by the Stefan Boltzmann law.
Okay, we're getting deep into the physics now.
I'll keep it simple. It basically dictates that you need massive, huge panels. The source gets very specific about this. They note that you can only reject about 600 to 1,500 watts of heat per square meter of radiator surface in space.
So if you are operating a 1 megawatt orbital data center.
You require thousands of square meters of deployed radiators.
Wow.
Which brings us to the mass penalty.
Right, because thousands of square meters of metal is heavy.
Very heavy. The analysis estimates that a 1 megawatt orbital IT load requires 30 to 50 tons of total mass.
50 tons for 1 megawatt.
Yep.
The source breaks that down a bit. Roughly 20,000 kilograms for the radiation-shielded compute servers.
Right.
8,000 kilograms of solar arrays to harvest the megawatt of power. And then another 8,000 kilograms of these massive deployable radiators, plus the spacecraft bus and propulsion systems to keep it in orbit.
Just massive structures. And to put that in perspective, think back to the Anthropic deal we discussed earlier.
The Colossus 1 deal.
Right. That involves roughly 300 megawatts of terrestrial power. To replicate that compute capacity in orbit, you would need to launch 15,000 tons of hardware into space.
15,000 tons. And launching mass into orbit is historically the most expensive transportation system ever devised by humans.
Without a doubt.
So let's run the economic model the author provides for space compute, focusing on the near-term baseline, like between 2026 and 2028.
All right, so for a 1 megawatt orbital cluster in this initial window, the hardware capital expenditure, the IT equipment, specialized cooling loops, and radiation-hardened enclosures is estimated at $200 to $500 million.
Wait, radiation hardening adds a huge premium, doesn't it?
Oh, massively.
Yeah.
Because beyond the Earth's atmosphere, these chips are bombarded by cosmic rays and solar radiation.
Stuff the ozone layer protects us from down here.
Exactly. Up there, a stray cosmic ray will cause bit flips in memory or just completely fry standard consumer electronics. You need specialized, expensive silicon housing.
Okay, so that's 200 to 500 million just for the gear.
Yeah.
And then you factor in the launch costs.
Right. If SpaceX's Starship is operational, and we assume an early, pretty optimistic launch cost of around $300 per kilogram to LEO.
Low Earth orbit.
Yes. A 42,000 kilogram payload costs about $12 to $15 million, just to put it up there.
And if the launch cost is higher, say $1,000 a kilogram.
Then that launch bill spikes to over $40 million per megawatt.
So the total upfront cost per megawatt in space right now, today, is sitting between $250 million and well over $600 million.
Correct.
How does that compare to building on Earth?
A terrestrial data center currently costs roughly $150 to $300 million per megawatt to build.
So orbital compute is starting out at a 1.5 to 3x capital premium.
It's way more expensive up front.
Yeah.
And there is a critical secondary factor, hardware lifespan.
Right. Because on Earth, you might run a facility for a decade, slowly upgrading components, swapping out bad hard drives.
Yeah, you just send a guy down the aisle with a cart.
But in space, the source notes an orbital server has a maximum lifespan of about 5 years.
Because the continuous radiation degrades the silicon over time, the thermal cycling going in and out of sunlight stresses the solder joints.
And you cannot send a technician to orbit just to swap out a failed RAM stick.
No, you just have to let it die. The source even models a 9% annual failure rate for the hardware in space.
Wow, 9% breaks every year.
Yes. So when you amortize that massive upfront capital cost over a really short 5-year lifespan, the levelized cost of compute, which is a metric that combines the capital and operational expenses to give you a true unit cost.
That must be severe.
It is. Early analyses put the cost of space compute at roughly $8 to $15 per GPU hour.
Which is astronomical, pun intended.
Right.
But seriously, terrestrial cloud rates are $2 to $4 on the spot market.
Right.
Even Google's totally desperate premium with SpaceX down here is 11.62.
Yeah.
So if space is hovering around $15 an hour and it breaks all the time, why would any hyperscaler actually pursue this?
Because the model requires you to look a decade into the future.
Okay, tell me about 2035.
The entire economic viability of orbital compute is a derivative of one single variable, the launch cost curve.
It all comes down to the rockets.
Always. Starship's ultimate design goal is full, rapid reusability, aiming to drive launch costs down to between $50 and $500 a kilogram.
If they can hit an optimistic target of, say, $100 a kilo.
Which is incredible.
Especially compared to the older Falcon 9 architecture, which sat around $1,500 to $3,000 a kilo. That fundamentally changes the math.
The author's model projects that by the 2030 to 2032 timeframe, as launch costs crater and satellite manufacturing transitions to true assembly line scale like making cars,
Right.
the upfront cost for a megawatt in space could drop to 150 to $300 million.
At that point, it reaches capital parity with terrestrial builds.
Exactly. It costs the same to build it in space as it does on the ground.
And the operational costs in space are virtually zero, right?
Yes, the solar power is free.
And the radiative cooling requires no electricity to run massive compressors.
So by 2035 and beyond, with extreme launch reuse and potentially lighter, more efficient radiator technologies,
The levelized cost of compute drops.
it could drop to $2 to $5 per GPU hour,
Wow.
effectively matching or beating terrestrial setups without ever having to wait for a grid interconnection queue.
Okay, I see the long-term mathematical trajectory there. If the rockets get cheap enough, the infinite free power of space eventually wins out.
It has to.
But there is a glaring technical problem here.
Latency.
Latency. The speed of light is a hard physical limit.
You can't bribe physics.
Exactly. If I am using an AI assistant on my phone, my prompt has to travel up to a satellite 500 miles away, get processed, and be beamed back down.
Right.
For real-time applications, that delay makes the service feel sluggish or basically unusable.
You are distinguishing between two very different types of compute workloads, inference and training.
Okay, what's the difference?
You were describing inference, where a pre-trained model generates a response to a user prompt, like asking ChatGPT a question. For inference, latency is critical, and those servers will always need to be geographically close to population centers, down on Earth.
Got it.
But space compute is not designed for inference, it is designed for training.
Ah, training the frontier models.
Exactly. When a hyperscaler trains a model like GPT-5 or Gemini, they lock a massive cluster of GPUs in a virtual room for 6 to 9 months,
They're just crunching data.
crunching petabytes of static data to determine the mathematical weights of the neural network. There is no real-time user interaction.
So nobody's waiting on a chat bubble.
Right, latency does not matter in the slightest. You just beam the data up, let it cook for 6 months, and beam the finished model back down.
So space is the perfect environment for bulk, asynchronous, power-hungry training workloads.
Exactly.
But even with that clarification, we are still talking about the mid-2030s for orbital compute to become truly economically competitive.
Yeah, it's a ways out.
The hyperscalers are bleeding cash today. They need power today. So space gives you limitless power and free cooling, but the rocket math doesn't work for another 10 years.
Right.
Is there anywhere on Earth that naturally mimics the freezing temperatures and limitless clean energy of space without needing a $40 million rocket ride?
This brings us to the most pragmatic, immediate proposal in the source material.
Okay.
A concept the author describes as a terrestrial space station,
I love that phrase.
the Himalayan Compute proposition.
The nation of Nepal.
Yes.
When I think of global tech hubs, I think of Silicon Valley or maybe the massive desert solar farms in Texas or data centers near the Arctic Circle in Scandinavia.
Sure.
Why would anyone try to build the computational engine of the world in the Himalayas? I mean, the logistics of traversing that terrain sound like an absolute nightmare.
It sounds deeply counterintuitive until you look at the specific geographic advantages.
Okay.
The two primary variables driving data center economics are electricity generation and cooling efficiency.
Right, power and heat.
Nepal possesses a structural geographical monopoly on both.
Let's start with power.
Okay, Nepal sits on one of the greatest untapped renewable energy reserves on the planet, the hydro potential of the Himalayan river system.
Water running down massive mountains.
Exactly, gravity and water. The source outlines the scale of this. The theoretical capacity is roughly 83 gigawatts.
83 gigawatts, that's huge.
And of that, about 42 to 43 gigawatts are considered economically feasible to develop.
And currently, they have only developed a fraction of that, right? Like a few gigawatts.
Just a tiny fraction. It is a massive, roaring engine of clean energy just waiting to be harnessed.
Wow.
And unlike solar or wind, which suffer from intermittency, they require massive, expensive lithium-ion battery banks to provide power when the sun sets or the wind dies.
Right, because the servers still need to run at night.
Exactly. Hydroelectricity provides reliable, dispatchable baseload power. It flows 24 hours a day, 365 days a year.
And because the water is doing the work through gravity, the generation costs are incredibly low.
So,
The source notes that retail electricity rates for business users in Nepal are currently sitting around 4 to 6 cents per kilowatt hour.
and that's retail. If you are building a massive hyperscale facility and negotiating wholesale behind the meter rates directly at the generation
Right
source.
next to the dam.
Exactly. That cost drops even further, potentially into the 1 to 2 cent range.
1 to 2 cents.
Yeah.
Compare that to constrained markets in the US or Europe, where commercial power can spike wildly and often relies on natural gas or coal for that kind of uninterrupted reliability.
It's an insane discount.
So you have baseload power that is an order of magnitude cheaper. What about the cooling? We talked about the thermodynamic nightmare of 120 kilowatt server racks and the auxiliary power needed to run massive liquid chillers.
Well, the Himalayas provide the second structural advantage. Extreme altitude.
It's freezing up there.
Exactly. The ambient temperature at high altitudes naturally replicates the cooling environments companies spend billions trying to artificially create.
Oh.
You can leverage ambient air economization.
Meaning you literally just open a window. Like you pull the freezing outside air into the facility to cool the water loops, rather than using electrically demanding compressors to chill the water.
Basically, yes. The wet bulb temperatures in the high Himalayas allow for free cooling for nearly the entire year.
That's incredible.
You strip out the 30 to 50% cooling overhead from your power budget entirely. The energy you buy goes purely into the silicon computation.
Let's run the back of the envelope math the author provides to see how this impacts the bottom line.
Let's do it.
We started this deep dive looking at Google paying SpaceX 11.62 per GPU hour.
Right. The author calculates that if your electricity is 10 times cheaper than a constrained Western grid, and your cooling costs drop to virtually zero.
The operational expenditure of the data center just plummets by 30 to 60%.
Meaning that 11.62 hourly rate could drop to $6 to $9.
Or potentially even lower, approaching the pure amortized cost of the hardware itself without the massive utility markup.
It creates the structurally lowest unit cost for compute globally.
Anywhere on Earth.
Yes. And because of this profound geographic advantage, the author proposes a highly specific business model to capture the market.
Okay, what's the pitch?
Himalayan Compute could offer the cheapest compute in the world, literally half the price of the prevailing spot market on one strict condition.
The hyperscalers have to commit and pay 3 years in advance.
That forward contract is the linchpin of the entire concept.
Because you need the money to build the dams.
Exactly. If a company like Microsoft or OpenAI pays 3 years up front, they lock in an unprecedented low rate, securing their runway for the next 3 generations of model training.
While massively undercutting their rivals' training costs.
Right. And in return, Himalayan Compute gets the massive upfront capital required to build out the concrete, the turbines, and the transmission lines.
It elegantly bypasses the grid constraints we discussed earlier.
Completely sidesteps them.
You aren't waiting 5 years for a U.S. utility company to build a substation. You are building the generation and the consumption infrastructure side by side in a sovereign nation that eagerly wants the development.
It's a win-win.
But building out 42 gigawatts of untapped hydro potential, that is not a startup pitch.
No, it is not.
That is a nation-building exercise. It requires capital on a scale that is almost difficult to comprehend.
The author estimates the total cost of developing 50 gigawatts of hydropower alongside the necessary high-voltage transmission lines and the data center infrastructure
Prepare yourself.
at approximately $110 billion.
$110 billion. Even for Silicon Valley, that is an astronomical figure.
It's GDP-level money.
The source breaks that down to roughly $2.2 million per megawatt. Who on earth writes a check for $110 billion for infrastructure in South Asia?
Well, the author outlines a master strategy to finance this, proposing an alliance between 3 distinct global entities,
Okay.
each holding a piece of the puzzle that the others desperately need. He calls it the tripartite alliance.
The tripartite alliance. Who are the players?
The hyperscalers, the Gulf sovereign wealth funds, and the nation of Nepal.
This is where the macroeconomic theory and the geopolitics of AI get really fascinating.
It's a masterclass in incentive alignment.
Let's analyze the incentives for each party, starting with the hyperscalers, your Googles, your Metas, your Microsofts.
Yeah.
What is their exact role in a $110 billion hydro project?
They bring the demand guarantee and the supply chain leverage.
Because they had the chips.
Yes. They have the multi-billion-dollar R&D budgets, and crucially, they hold the privileged allocations for the NVIDIA chips.
Right.
They are the only entities capable of signing a binding agreement that guarantees if you build a 50-gigawatt facility, it will be instantly filled with the latest hardware and utilized at 100% capacity for years.
And in return, they get the cheapest GPU hours on the planet,
Exactly.
allowing them to train 10 trillion parameter models without bankrupting themselves on utility bills, while completely sidestepping the regulatory gridlock of Western power grids.
They secure the fundamental strategic resource of our era, abundant, uninterrupted energy.
So, okay, now we look at the second pillar, the Gulf sovereign wealth funds. We are talking about massive state-owned investment vehicles like Saudi Arabia's Public Investment Fund, or the PIF, and Abu Dhabi's Mubadala and ADIA.
They bring the actual cash.
Yeah, they are sitting on trillions of dollars in liquid assets generated from decades of global fossil fuel exports.
Trillions.
But why would they pour $110 billion into a dam in Nepal instead of, just building AI hubs in their own deserts?
Because their primary strategic mandate right now is post-oil diversification.
They know the oil won't last forever.
Exactly. They recognize that the era of fossil fuel dominance has an expiration date. They need to transition their immense wealth into the industries of the future to secure generational revenue.
Right.
A mega project like Himalayan Compute offers them everything they require: long horizon, inflation-protected infrastructure assets.
And it carries massive ESG, environmental, social, and governance credentials because it is 100% renewable hydroelectric power.
Which is huge for them.
It allows them to pivot their portfolios from carbon-heavy oil directly into the green bedrock of the AI revolution.
It is an impeccable matching of needs.
Yeah.
The hyperscalers need power but don't want to become utility companies. The sovereign wealth funds need a green, future-proof asset to park hundreds of billions of dollars.
And the structure of the deal, the 3-year advance payment from the tech giants?
That fundamentally de-risks the project for the Gulf investors.
Because they aren't guessing if it will make money.
Exactly. They aren't building a $110 billion dam on speculation. They are building it with guaranteed, locked-in revenue from the most credit-worthy companies in human history.
And the third pillar of this alliance is Nepal itself.
Right.
They provide the geography, the water, the extreme altitude cooling, and the supportive policy environment to make it happen.
The physical foundation.
What does a developing nation get in return for handing over its natural topography to tech giants and foreign wealth funds?
The economic impact would be completely transformative.
How so?
It provides massive foreign direct investment, the creation of high-tech and infrastructure jobs, widespread technology transfer, and an incredible stream of export revenues.
Because right now they just export electricity, right?
Yeah, instead of simply exporting raw electricity to neighboring countries at low margins, they're exporting the highest value commodity on Earth. Process computational intelligence.
They become the computational engine room of the 21st century.
Precisely.
I have to push back on the optimism here, though.
Fair enough.
Developing $110 billion of infrastructure in a developing nation carries immense geopolitical and execution risks.
Oh, absolutely.
Building 50 gigawatts of hydro isn't just pouring concrete. You have to run a high-voltage, direct current transmission lines across some of the most rugged, mountainous terrain on the planet.
It's an engineering nightmare.
You have to ensure absolute political stability for decades. You are asking Microsoft and Saudi Arabia to trust their most critical intellectual property to a facility halfway across the world.
Those risks are material and severe. Logistics in the Himalayas are notoriously difficult, and the geopolitical complexities of South Asia cannot be ignored.
Right.
However, the author's thesis is that the sheer magnitude of the AI power bottleneck forces these companies to accept risks they would have previously dismissed out of hand.
Because the alternative is just stalling out.
Exactly. The alternatives, waiting 5 years for U.S. grid interconnections or launching servers into orbit at a massive premium, make the Himalayan proposition not just viable, but necessary.
It also acts as a geopolitical hedge, doesn't it?
How so?
Well, right now, a massive percentage of global compute capacity is concentrated in a few key U.S. states, like Virginia or centralized European hubs.
Right. Ashburn, Virginia is basically the internet's hometown.
Exactly. By moving 50 gigawatts of capacity to South Asia, the hyperscalers create strategic geographic resilience.
They don't have all their eggs in one basket.
The ultimate takeaway from this analysis is that the paradigm of the technology sector has inverted.
It really has.
For decades, value is created by writing more efficient code. by purely intellectual labor. Two guys in a garage writing software.
Right, the classic Silicon Valley mythos.
But the winner of the AI race will not simply be the company with the most elegant algorithms. The winner will be the entity that commands the physical leverage to generate electrons.
It's back to heavy industry.
We started this journey looking at Google handing over $1 billion a month to SpaceX just to avoid a delay in plugging their servers into the wall.
Which still blows my mind.
We explored the thermodynamic realities that are pushing the global grid to the breaking point, and the multi-decade plan to utilize the vacuum of space and the limitless solar energy of orbit to bypass terrestrial utilities.
And we grounded those sci-fi ambitions back on Earth, unpacking the economic and geographic logic of a $110 billion tripartite alliance designed to turn the freezing altitudes and roaring rivers of the Himalayas into a terrestrial space station for artificial intelligence.
It fundamentally redefines how we view infrastructure. I want to emphasize why this matters to you, the listener.
Yeah, bring it home.
Because it is easy to get lost in the abstraction of gigawatts and sovereign wealth funds. But the AI revolution, the medical breakthroughs, the automation of logistics, the digital assistants you interact with daily, none of it is ethereal.
It's all physical.
Every single prompt you type, every image generated is physically tethered to heavy industry. It is bound by the brutal realities of thermodynamics, water turbines, cooling towers, and concrete.
The intelligence shaping our society is a manufactured physical product.
We are witnessing the industrialization of cognition.
That's a great way to put it.
We began by talking about how an entire human brain runs on just 20 watts of power, a biological miracle.
Right.
And now we are building a digital brain that requires the electrical output of entire nations just to function.
That's a sobering thought.
So I want to leave you with this to mull over. If computational power is the new oil, the fundamental resource of the 21st century, and the geographical centers of that power are shifting away from the mild climate of Silicon Valley to places with extreme natural energy abundance, like the high-altitude rivers of Nepal, or even the cold vacuum of low Earth orbit, how does that redefine global wealth and geopolitical power in our lifetime?
Who really dictates the future when the smartest mind on Earth is physically tethered to a waterfall in the Himalayas?
Exactly. Thank you for taking this deep dive with us.